Welcome again, you all, in this session of fluid mechanics and fluid machines. In the last lecture, we studied the impact of a jet on a moving vane when the jet of water strikes the moving vane tangentially at one of the end. I am again briefing about the same again. What we did in the last class, there was a vane. The vane was moving, the single vane, a single vane. Vane was moving with speed u or velocity u in x direction. The jet of water struck at one of its end, tangentially at one of its end. Since we know that since the blade is moving, the jet will strike with some relative velocity Vr1. At inlet, I am using subscript of Vr1. The jet will strike the vane with relative velocity Vr1. And this vector addition holds good over here. Vr plus u is equals to absolute velocity. Vr vector plus u vector is equals to v vector. So I simply added u vector over here with the tail of Vr, and this I got absolute component of velocity v1. This is the blade velocity u1. Since u1 and u2 are same, so this is u. This angle came to be known as alpha, nodal angle, and I made two components of v1. One is along the motion of the vane, in the direction of motion of vane, which is known as whirl component vw1, and one component is perpendicular to the direction of motion of vane, that is vf1. Vf1 is known as the flow velocity at inlet. Vw1 is known as velocity of whirl at inlet. That's what we have seen. This angle is theta, which is the blade angle at inlet. Same thing I did for the exit. Likewise, the jet would be leaving with relative velocity Vr2. The jet would be leaving some relative velocity Vr2. Now, I have to add this u in this Vr2. For that, this u has been added into Vr2. The tail of u has been added with the head of Vr for this vector addition. Now, this will represent the absolute velocity v2 at exit. Again, this angle is phi, the blade angle at the exit. Two components of v2 are there, vf2 and vw2, and this is u again. So that's what we have understood. This angle is beta. This angle is beta. Now, that's what we have seen in the last class. Where the jet of water was striking a moving vane tangentially at one of its end. For this case, I determined force exerted in the direction of motion of vane by the jet of water as m dot vw1 plus vw2, and the work done on the vane in the direction of motion of vane was written as m dot vw1 plus vw2 into u. Note, the point to be noted over here is that the mass flow rate will be rho a vr1 because the jet of water is striking single vane with relative velocity vr1. So this is a case of a single vane when the jet of water is striking the single vane at one of its ends tangentially. Now we will observe an important concept that might be a next case, that is when the jet strikes a series of vanes. Now the concept of series of vanes, not a single vane, rather than the series of vanes, which is also known as a concept of runner. Means now there is not a single vane, rather than a number of vanes are mounted on a wheel. Please observe again, listen to me very carefully. Now I am going with the in the previous lecture, in the previous case, we did for a single moving vane. Now we are dealing with the concept of a series of vanes which are mounted on a wheel. When a series of vanes are mounted on a wheel, then it becomes a runner. So either you can say concept of series of vanes or concept of runner. When a series of vanes are mounted on a wheel, then what happens? Observe. First of all, we have to note a very important point over here. For example, let this is a runner or a series of veins are mounted on the runner. This is a case of, sorry, series of veins. So in this case, in case of series of veins, what happens? The mass flow rate is taken as rho a v1. Please note, not VR1, because when the jet strikes one of the vein, the another vein comes in front of the jet. So always there is a vein ahead of the jet. Getting the idea or not? Please observe, when the jet is striking one of the vein moves forward and another vein comes in contact with the jet. So what jet finds, there is always a vein ahead of the jet or in front of the jet. That is why the whole mass flow rate issuing out of the nozzle is utilized by the veins. Please again observe whatever I am saying. The mass flow rate in this case of series of veins would be taken as rho AV1 rather than rho AVR1. We will use the absolute velocity of jet rho AV1. Why? Please observe. When the jet is striking one of the vein moves and another vein comes in front of the jet. So this case becomes like that. A jet is striking always a stationary vein because always there is a vein ahead of the jet or in front of the jet. So whatever the discharge is issuing out of the nozzle will be utilized by this series of veins. Therefore, the mass flow rate which we will take is equals to rho a v1, and the formula for Fx would become rho a v1 Vw1 plus Vw2 multiplied by U. So in case of a single vein, we will use this mass flow rate when the jet is striking tangentially at one of the end, and in case of a series of veins, when the jet is striking the veins tangentially, then we will use this formula for mass flow rate, rho a v1, and Fx will then become rho a v1. I am again repeating why I have used absolute velocity. I have used absolute velocity because whatever the mass flow rate is issuing out of the nozzle, that would be utilized by this series of veins. When the jet will strike one of the vein goes and another vein comes in front of the jet. Therefore, whatever the discharge is issuing out of the nozzle will be utilized by the veins. Therefore, we will have mass flow rate as rho AV1 and force will be rho AV1 Vw1 plus Vw2 into U. I think it is very much clear to you. Now dear, we will study the concept of radial curved veins. Let's study the concept of radial curved veins or series of radial curved veins. Series of, another case you can take, series of radial curved veins. Series of radial curved veins, or we can say the concept of radial flow runner. Concept of radial flow runner. Both are the same heading. Concept of radial flow runner. Now observe this point very carefully. The radial flow runner, the two headings are same. In some of the book, it is written that series of radial curved veins. Some of the book use the concept of radial flow runner. Both the concepts are same. Means a number of radial curved veins are mounted on a runner or a wheel, which comes to be known as radial flow runner. So let's observe a simple diagram for this radial flow runner. Let's see. There are two types of radial flow runners. One is inward flow runner, another one is outward flow runner. Let's observe. I am showing you the top view. I am showing you a top view. For example, this is a runner and a number of veins are mounted on the runner. Number of veins are mounted on, this is a wheel, a number of veins are mounted on the wheel. Then it is known as a runner. This is the axis about which the runner is rotating. This is the axis about which the series of moving vanes or the runner is rotating. This is the axis. This is the axis perpendicular to the plane of paper about which the runner is rotating. Now dear, there are two cases in this case. Either the water may enter at this smaller radius and may leave like this. There are two cases. This may be inlet, this may be outlet. Such a case is known as, this case is known as outward flow runner. Outward flow, radial outward flow runner. This case, observe, when the water enters at the smaller radius and leaves at a larger radius. This radius is r1, this radius is r2. So when the water enters at a smaller radius, leaves at larger radius, then it is a radial outward flow. This is, you can observe, this is a radial outward flow. This is the radial outward flow. The inlet is over here, exit is over here, so this is a radial outward flow. Radial outward flow. Observe along the vein. This is the radial outward flow along the vein. Another important case is here. Observe within this diagram only. When the water enters at the larger radius and leaves at the smaller radius. The inlet is this. Since I have already told you that one will be used for inlet and two will be used for exit. So when the water enters the vein or water enters a blade at a larger radius and leaves at a smaller radius, then it is known as radial inward flow runner. Radial inward flow runner. Radial inward flow runner. Okay, we are observing the radial flow runners in which the flow is in a radial direction. In which the flow is in radial direction. Either the flow is in a radial outward direction or the flow is in radial inward direction. So this case is radial inward flow. This is for radial outward flow. I think it is clear to you. Now let this is radius r1 and this is radius r2. Now we can clearly note that over here in this radial inward flow runner, if I want to write the speed of the velocity of blade at inlet and exit, velocity of blade, observe this radial outward flow runner. This radius is r1, this is rotating with angular velocity omega. The runner is rotating with angular velocity as the jet works on this runner. The runner is rotating with angular velocity omega. Therefore, the blade velocity at point 1 will be omega r1. Blade velocity at inlet, that is u1, will be equals to omega into r1. And the blade velocity at exit, blade velocity at exit, u2 will be equal to omega r2. Please observe this point. I am talking about radial outward flow runner. This is the inlet, this is the exit. So inlet radius is r1, exit radius is r2. So blade will be moving with different tangential velocities. Tangential speeds of the blade at point 1 and 2 will be different. That will be omega into r1 and omega into r2. Omega into r1 and omega into r2. For radial inward flow runner, observe this is the inlet, this is the exit, because the flow is radial inward. Therefore, u1 will be equal to u1 omega r2. Please observe. And u2 will be omega into r1. I think it is very much clear. For this particular case, I have done this to make you understand. In this case, this is blade velocity at inlet, blade velocity at exit. This is u2. I think it is clear to everyone. Now let's see each and every concept in a different manner. See, let me talk about an inward flow, radial inward flow runner. Radial inward flow runner. Radial inward flow runner. For inward flow, I have to draw like this. Observe. This is the whole runner. This is the whole runner. Whole runner is there. Whole runner. I am drawing only a single vein over here. I am drawing a single vein. I am drawing a single vein. I'm drawing a single vein. Now we know that this is the inlet and this is the exit. This is the inlet and this is the exit, because the flow is radial inward. The flow is radial inward. So this is the inlet to the vein, this is exit to the vein, because the flow is radially inward. Let the runner is moving with angular speed omega. Therefore, the speed of the blade at inlet and exit would be different. The speed of the blade at inlet and exit would be different. This will be the speed of the blade at inlet u1, omega into radius r1. Omega into r1 is u1. Omega into r2. Omega into r2. This is the radius r2. So omega into r2 is the u2. Perpendicular to this r2. This is u2. I think it is clear to you. I have determined u1, u2. u1 and u2 are different because the jet is entering at larger radius and leaving at a smaller radius too. Therefore, speed of the blade at this point 1 will be u1, which is equals to omega into r1, and u2 is equals to omega into r2. So now I have to draw the velocity triangles for this case. The velocity triangles are very easy to do. Observe. Since we have already talked that when the jet strikes tangentially, then in that case the component of relative velocity will be tangential to the vein. This component of relative velocity Vr1 would be tangential to the vein. This is the component of relative velocity Vr1. Sorry. If u1 is added into this Vr1, then we have to go with this vector addition. Vr u is equals to v, both at inlet and exit. So I have to add, this is the vector Vr1. This is vector Vr1. I have to add u1 in this. So just draw u1, place u1 over here for this vector addition. Just place u1 over here. I have placed simply u1 over here in the same direction. Whatever the direction of u1 is there, place u1 over here so that the head of the u1 is connected to the tail of Vr1 to complete the vector addition. Then this will represent the absolute velocity v1. This will represent the absolute velocity v1. This is the nodal angle alpha. Now again I have to make the two components of v1. One is in the direction of motion of the blade, which is known as vw1, the whirl velocity, and another component is this along the radius. Another component will be along the radius r1. This component is known as vf1, the flow component. The flow component of the velocity will always be in a radial direction to signify that the flow is a radial inward. This is the flow component which will be along this radius r1, flow component of velocity vf1. This angle is the blade angle at the inlet. Blade angle at the inlet. This is nodal angle. There are two components of v1, vw1 and vf1. Vw1 is in the direction of motion of the vein and vf1 is the radial component along the radius to signify that the flow is in radial direction. Now velocity triangle at the exit is very easy again to draw. Very easy. Just observe. The jet of water will leave radially. Sorry, the jet of water will leave tangentially. So this is Vr2. This is Vr2. Tangentially, the jet of water will be leaving. This is Vr2. We add u2 in Vr. This I have added u2. Sorry. This is u2. This is Vr2. This is u2. If Vr2 and u2 are added, this component would be, sorry, this is u2 whole. Then this component would be v2. Observed here. The jet is leaving tangentially to the vein with relative velocity VR2. In VR2, I have added U2. U2 has been added into VR2. This U2 has been added. This is U2. I have put simply U2 from here to here. Then this will represent the absolute velocity of water. Now again, this absolute component of velocity will be having two components. One is along radial direction, which is Vf2, and this is Vw2. This is Vw2. This angle being phi, this angle being beta. So this is the velocity triangles. These are the velocity triangles for a radial flow runner. Velocity triangles for a radial flow runner. I think it is very much clear to you all. The velocity triangles are similar to that of a single vein case. The velocity triangles are similar to a single vein case. You have to draw in this fashion only. Now, for this case, I am not deriving expression, rather than I am simply writing that the work done on the vein is given by W equals to m dot Vw1 plus, work done is given by m dot. Now since u1 and u2 are different, we will simply write Vw1 u1 plus Vw2 u2. You yourself have to derive the expression, this expression. You yourself have to derive this expression. Mass flow rate, you will observe in case of jet, this mass flow rate, this is a series of veins, so mass flow rate will be rho a v1 rather than rho a vr1. So mass flow rate will be rho a v1 in case of radial curve veins. Clear? So this is the expression for work done in this case. Simply write Vw1 u1 plus Vw2 into mass flow rate. This expression you have to derive yourself. It is very easy to derive. Whatever we have done in the earlier case, in the same manner you have to derive this expression. But since now u1 and u2 are different, therefore the expression becomes different. Now we will talk about the radial outward flow runner. Sorry, one thing I left. Here you can observe that u1 equals to omega into r1. R1 is moved. u2 is equals to 0.2. u2 is equals to omega into r2. And observe that u1 is more than u2 since r1 is more than r2. Since r1 is more than r2, the water enters at the larger radius, leaves at smaller radius. Therefore, r1 is more than r2. Therefore, u1 is more than u2. Now, the next case, radial outward flow runner. This will be drawn like this. Now this is the vein. This completes, this is the whole runner. I am showing only a single vein. Now radial outward flow. This is the center. This is the axis about which the runner rotates in this direction like this. So water enters at this point. This is the entry point. This is the exit point. So this is radial outward flow. This signifies radial outward flow. Radial outward flow. Now observe. In this case, this is radius R1. This is radius R2. So this will be U2. Perpendicular to R2 will be U2. U2 will be omega into R2. This will be U1. Perpendicular to R1, omega into R1. So you can write that since R2 is greater than R1, therefore this U2 will be more than U1. The blade speed at exit would be more than blade speed at inlet. It is just reverse of inward flow. In inward flow, we had U1 greater than U2. because entry is at the larger radius, the exit is at a smaller radius. Over here, the entry is at a smaller radius, the exit at larger radius, therefore u2 is more than u1. The velocity triangle we have to draw. It is very easy to draw. Again, we have to start with the VR1. Let this is VR1. Tangential to the, for no shock condition, the relative component of velocity must be tangential to the vane. Add u1 in this. This u1 has been added in this u1. So this I will get as, sorry, v1, absolute velocity at inlet. Now there are two components of v1. There are two components of v1. One in the direction of motion of the vane, which is known as vw1, whirl component. This is, and another one is the perpendicular to the direction of motion of vane, which is in the radial direction, which is known as vf1. This is vf1, flow component. Again, the angles are same. This is the nozzle angle at inlet. This is the blade angle at inlet, theta. Same you have to draw for the exit. Observe, the water will be leaving tangentially. So the water leaves tangentially. The relative velocity is vr1. Add u2. This u2. Now this will be v2. This will be v2. Then two components of v2. One along the direction of motion of the vane. Another one is in radial direction. Again, two components of v2. This is vf2, radial. Flow component is in radial direction to signify the radial flow. This is vf2 and this is vw2. This is vw2. Again, this angle is phi, blade angle at exit, and this angle is beta. So velocity triangles are again similar. So I think now 3 or 4 times we have seen to draw the velocity triangles. I think it is very clear to you all to draw the velocity triangles. The work done on the vane per unit time, work done per second on the runner. If I want to write the expression, then W will be equals to m dot vw1 u1 plus vw2 u2. How to calculate u1 and u2 I have already written over here. This is the concept of radial flow runner, radial outward flow runner. So we have completed the chapter of the impact of jets. In the next chapter we will be starting with the turbines, where we will see the Pelton wheel turbine, Francis turbine and Kaplan turbine. So to understand the turbines, you have to understand these velocity triangles very carefully. So last 2 minutes I am again revising the concepts. Just observe. First of all, we did for a single vane. A jet of water striking a single vane tangentially at one of the end, and vane was moving with velocity u. The velocity triangles we drawn, you have to practice these velocity triangles, and we observed that the work done per second on the vane is given by the formula m dot vw1 plus vw2 multiplied by the speed of the blade. vw1 and vw2 are the components of absolute velocity at inlet and exit in the direction of motion of the vane, or these are known as whirl velocity or component of whirl velocity. And m dot in case of a single vane is given by rho a vr1. But when we talk about a series of vanes, that is a concept of runner. Series of vane mounted on a wheel, then it is known as a runner. In that case, mass flow rate we have to take as a rho a v1 rather than vr1, and the formula for force will remain the same. Then we started the concept of radial flow runners. In this radial flow runners, there are two types of runners. One is radial inward flow, another one is radial outward flow. This is the radial outward flow. When inlet is over here, exit is here, radial outward flow. You can observe this is the radial outward flow. And this is the radial inward flow. When the inlet is at a larger radius, exit is a smaller radius, this is radial inward flow. For both the cases, we have drawn the velocity triangles, and also we have written the formula for work done. Okay, thank you.